This presentation is designed to cover the architecture of the data acquisition system for recording of steady-state visual evoked potentials. The steady-state evoked potential is a brain response elicited by a repetitive stimulus of a fixed frequency. During the stimulation, the steady-state response appears in the electroencephalogram (EEG) in a form of periodic, nearly sinusoidal waveform of the same fundamental frequency as the stimulus. Often, it includes higher harmonics. Depending on the nature of the stimulus, steady-state potential can be visual, auditory, or somatosensory potential. In the case of steady-state visual evoked potentials, the subject looks at the light flashing source, such as light-emitting diodes. EEG electrodes placed on the head register brain activity. An example of amplified EEG signal for electrodes positioned in the occipital region is presented in the figure left top. The frequency of stimulator was set to 15 Hz. The corresponding power spectrum is presented in figure left bottom, and the peak on 15 Hz is visible as well as higher harmonics. An EEG system setup that we used for the demonstration is presented in the video on the right side. A 14-channel EEG emotive epoch device with semi-dry electrodes was used. This device acquires EEG data and sends it wirelessly to the computer for further processing and data lodging. Now, a simple EEG data acquisition application using emotive epoch and LabVIEW will be described in detail.
For this exercise, we are not going to make a code for acquisition of EEG data, but we are going to look the example that LabVIEW provides when we install emotive toolkit. So I'm going to open this code, and front panel opens. We have two graphic indicators and one path control here, and of course stop button. This control specifies the path to EDK file that we have to communicate with the device we have. This graphics shows sample count in our EEG signal that we acquired, and this graph here shows us all EEG signals from all the electrodes we have choose. After we saw how a front panel looks like, let's see how block diagram looks like. In the first look, we can see that this structure is very similar to structure for basic data acquisition. Only the blocks are called a little bit different, and the stuff in the while loop is a little bit different. So first, we have this create task for emotive. I'm going to open the context help so we can also see that there. And as its input, we have to specify which EDK-DLL file we are going to use. So we have a control to insert the path to this EDG-DLL file. After that, we need to start emotive task. And in this part of the program, we are connecting to the device we have, so emotive. Third step is start data acquisition. We initialize the buffer and we say how much is our buffer size in seconds. So in this way, we are going to hold only 2 seconds of data. In the while loop, we have this data acquire data block. So in this block, we are collecting or reading the data from the emotive that is in the buffer and clear the buffer. After the while loop, we have emotive stop task block that is used to stop the task and free allocated memories and so on and so on. Okay, so this part of the program tells us how many channels does our device have. In this example, we have 14 channels for EEG, and that is how much we are going to read in our while loop. This while loop is refreshed every 50 milliseconds. That is with this block specified here. And of course, like every while loop, when the user presses the stop button on the front panel, the while loop stops. Okay, so as the output of this block, we have 2D array, so a matrix in which first row is sample count and all the other rows are EEG data. So we need to divide this matrix to one row of sample count and other rows for EEG data, other 14 rows for EEG data. After we get this 14 rows, or I think even more, because we are not only gathering samples from the electrodes on our emotive, but also from these 3 parts. We have these 3 things here. So we are going to eliminate those in that way that we are going to tell that we are going to use only third element as our starting point for our array subset, and we are going to have 14 elements of length. So here we have this 14 elements that corresponds to 14 electrodes on our emotive device. We subtract this constant of 4000 and save that data in this EEG data graph, show that data. So we have a chart that has all 14 electrodes that are placed here. We can show the data all in one graph, or we can divide this into different. So we are going to say stack plots, and he's going to divide this into 14 smaller graphs. Okay, so in the first iteration, when iterator is equal to 0, we are going to clear the graph. So we are going to set the plot name and see which plot is active. And when it's false, we are not going to do anything. Okay, so this is quick demonstration of how the block diagram for basic emotive data acquisition looks like. After this, when we have the EEG data, we can do some analysis like detection of alpha waves or spectrum analysis, what we need. But this is the first step for creating that kind of application. Okay, thank you everyone for listening, and see you in the next video.
Steady-state visual evoked potentials can be used as control signals in brain-computer interface systems, so-called BCI systems. Each command in the BCI menu corresponds to the repetitive visual stimuli presented to the user. Our students Maja Pantic and Jelena Jakšić designed such a system. During their experiment, the subject looks at the light-emitting diode, and the application acquires EEG signals from 4 electrodes positioned in parietal and occipital regions. Real-time monitoring of EEG power spectrum is implemented, and the small Arduino-based spider robot will move if steady-state visual evoked potential is detected. On this slide, at the left side, you can see the graphical user interface with EEG power spectrums in parietal and occipital regions when the frequency of visual stimulus is set to 13 Hz. On the right side, the demonstration of the realized BCI system is presented.